last talk is by Aluna Rizzoli from Imperial College London, and he will tell us about groups, representations, and applications, new perspectives.
Okay. First of all, thank you to all the organizers for giving me this opportunity. And I would also like to especially thank all the previous speakers, especially the ones that gave all the definitions that I'm going to need. Okay, so let's begin with some notation. We're working with algebraic groups over algebraically closed fields of characteristic P. We use Tn to denote an n-dimensional torus. Usually we use P to denote a parabolic subgroup and B a Borel. And if we have a root system phi indexed by some alpha i's, then the lambda i's are the fundamental dominant weights, and the G of lambda I is an irreducible rational G module of the highest weight lambda I. Okay, so given this, we can already describe the motivating problem behind our research. So we start with G, just a simple connected algebraic group over our algebraically closed field K. And we consider two closed connected subgroups, H and K, of G. So in general, the set of double cosets is just given here, the set capital H little g K for all G and G. And the question we're interested in is a very simple one: is this set finite or not? So this is a question that already produces many interesting examples, and we're trying to expand on some of these. So let's look at some of these cases. So when do we get a finite number of double cosets? Well, of course, if both H and K are Borel subgroup, or indeed a parabolic, since they contain Borels, then by the Dirac decomposition, we're going to get finitely many double cosets. Okay, one case we will look at into a little bit more detail occurs when G is just SLB, so type AN. Another case occurs when one of the where we only have one double coset. So of course, this means that the group G factorizes as HK, and we have some examples. So SO7 is G2P1, or SO8 is B3P1, where the natural 8-dimensional module V restricted to B3 is the spin module for B3. Well, the good thing is that these factorizations have been classified already. And another important class of examples occurs when both H and K are reductive. Then if we have a finite number of double cosets, then there's actually only a single double coset, and we are in the previous case where we have factorization. And okay, so if we want to look at this problem with H and K maximal, let's say, we can assume that K is a parabolic, because, of course, if you're not reductive, you're going to be contained in a parabolic. So with our maximality assumption, we can make an assumption that K is a parabolic. Okay, so I promised we would talk about the case where G is the special linear group. Okay, so we have G being the special linear group, and K is a maximal parabolic. Well, a maximal parabolic is just going to be a stabilizer of an M space. So what are we looking at to solve our question? We're looking at the cases where H acts with finitely many orbits on M spaces. Well, there's a list of all irreducible modules for semi-simple algebraic groups with finitely many orbits on M spaces. And when we're talking about orbits on one spaces, we call these finite orbit modules. Okay, let's take a look at what the theorem originally said for finite orbit modules. So this was the original statement. Okay, so over an algebraic closed field, we have the irreducible rational finite orbit KG module. And either it is an internal module, I'll tell you what internal modules are,
or it is one from the following list. So we have G, written in terms of the root system. V, we just denote V by the fundamental dominant weight, dimensions, and some conditions on P. Just as an example, you can look at AN. This is a particular case because, well, the module has dimension, well, one of these two modules, so lambda 1 plus p to the I lambda 1, or lambda 1 plus t to the I lambda n, when p is greater than 0, they have dimension n plus 1 squared. So the dimension of the variety of one spaces is n plus 1 squared minus 1, which is precisely the dimension of the group G. So the dimension is just exactly enough for it to have possibly finitely many orbits on one spaces, which indeed is the case. And we're going to have an analogous case for our theorem when we'll take a look at not G being SLN, but G being the special orthogonal group. OK, what are internal modules? Well, there are a class of modules that are always going to give us finitely many orbits on one spaces. You can take an algebraic group, a parabolic with Levy subgroup G, a G-invariant composition series for the unipotent radical Q, and then just quotienting Qi plus 1 over Qi, we're getting rationally irreducible Kg modules. And in fact, in general, the Levy subgroup G has finitely many orbits on each module. So this gives us the big family, and you can list all the internal modules. So that's not a problem. A quick example of an internal module. So in E7, if you delete the 6 node, you're getting an A1 and a D5. Well, that's the semi-simple part of the Levy factor. So the module is just a tensor product of the natural module for A1 and the spin module, the half spin module for D5. And well, we immediately get that G has finitely many orbits on one spaces. In fact, we can say a little bit more. We have that the number of G orbits on one spaces is 2, which corresponds to the orbits on simple tensors, plus the number of orbits of D5 on two spaces. And in upcoming work, we see that there are 6 orbits on two spaces in the half-spin module. OK, let's look at our setting. So a natural first step after the case where G is the special linear group would be to look at another classical group. Of course, if you take the symplectic group, and you're still thinking about one spaces, then you're not going to be thinking about anything new, because the well, P1 parabolic in the symplectic group is just going to be the stabilizer of a singular one space, which is, and all vectors are singular. So we take a look at SON, the special orthogonal group, and the P1 is a subgroup stabilizing a singular one space. So we're looking for groups acting with finitely many orbits on singular one spaces. And this is the theorem. So if we have H, which is a closed connected subgroup of G, acting irreducibly on V, with finitely many orbits on singular one spaces. So if it was already a finite orbit module, of course, if you're already a finite orbit module, then you're going to have finitely many orbits also on singular one spaces. Or we have a little family of cases arising from composition factors of the adjoint module. We'll take a look at these later. Or you are in a finite list of things. So we have 5 cases ranging from A1 to F4. And well, you can immediately notice that we only have one case, i.e. the first one, where we get a stabilizer which is finite. And we start by taking a look at this interesting case. OK, so let P be greater than 5, and let's take H to be SL2K. Then the module is just going to be obtained by taking a natural two-dimensional module for H, take the 4 symmetric power, we get a irreducible 5-dimensional module. And, well, this wasn't a finite orbit module, and there's an obvious reason, and it's that the dimension of A1 is 3, which is strictly less than the dimension of a variety of 1 spaces. But indeed, V is an orthogonal module, which means that the embedding, H embeds as a subgroup of SOV. And indeed, the quadratic form is just going to be obtained in the usual product way. And, well, again, by dimensional considerations, well, the dimension of the variety of singular 1 spaces is the dimension of V minus 2. This is precisely the dimension of A1. So if we have, as it's going to be the case, a finite singular orbit module, then we need a finite stabilizer. Okay, how can we show this? Well, 2 orbits are easy to find. If you just take E tensor with itself 4 times, this is fixed by a P1 parabolic in A1. And if you take another basis vector, this is only fixed by T1. So we have 2 relatively obvious orbits with their stabilizers. Okay, so if we want to do some counting, we need to go down to finite fields. So the idea is to find another orbit and then show that these 3 orbits are precisely all the orbits. Okay, so these 1 spaces are both singular, so that's helpful for us. Okay, so we start by taking a subgroup, the subgroup alternating 4 of H, and we can assume we're working of the algebraic closure of FQ. It doesn't generally matter which field of algebraically closed field you're working with, as long as the characteristic is the same. And, well, you can see that this finite group alternating 4 is fixing 2 singular 1 spaces, and it's the full stabilizer of these 1 spaces. Okay, so once we know that, we, but just using some Lang-Steinberg theory, we go down to finite fields, and we observe that when Q is congruent to 1 mod 3, we're getting that this orbit, so the orbit with the stabilizer alt 4, splits into 4 orbits, and otherwise it splits into 2. And the sizes of the stabilizers are as listed. So we have 3, 3, 4, 12, and 2, 2. But now that we have the sizes of these stabilizers, so how the dense orbit is splitting, and the previous ones, then we can add everything up. And we in fact get the number of singular 1 spaces. In fact, proving that, well, in general, we are only going to have, in the algebraic case, we only have 3 orbits on singular 1 spaces. Okay, so let's go back to our list. We discussed A1, and I would like to take a look at B6. So B6, lambda 6, what is it? It's the spin module for B6. It's actually the unique irreducible rational module of dimension 64 for B6. Well, just as a quick mention for those of you who haven't seen spin modules before, you can take the Clifford algebra of the natural 14-dimensional module for D7 and look at the embedding of B6 in this Clifford algebra, and then there's a natural action on the spinors. Okay, and well, note that also in our conditions we had a P equals 2, and this is needed for the module to be orthogonal. Okay, I don't want to scare you with this table and other upcoming tables. You don't need to take anything away from this. But the point is that we already had a list of D7 representatives for the orbits on the spin module. And, well, it was in characteristic 0, and in fact, it holds as well for characteristic 2. And what do we do? Well, B6 is just a stabilizer of a non-singular 1 space in D7. So one can just take every single stabilizer and look at the orbits on non-singular one spaces. This tells you how each D7 orbit splits. And again, don't take anything away from this, just maybe note the G2, so this was the dense orbit for the D7 action. And so this orbit splits into infinitely many orbits on one spaces. So when you restrict to B6 on this dense orbit with stabilizer G2 has infinitely many orbits on one spaces, but this infinite family, so with these representatives, does not produce infinitely many singular one spaces. So in fact, we just check that all these infinite families, where we have these coefficients, they do not produce infinitely many singular one spaces, and this shows that indeed in the B6 action on singular one spaces, we only have finitely many orbits. Okay, so I just wanted to share a bit of the fun I had with the spin modules. Now, in the theorem, I talked about the possibility of having composition factors of the adjoint module. Why are these special? Well, first of all, the adjoint module, just look at it as the Lie algebra of H, on which H acts by conjugation. And in the case of the special linear group, we have the Lie algebra SLN of trace zero matrices. And when P does not divide N, this is an irreducible module. Is not an irreducible module because, of course, scalar matrices are going to be fixed by conjugation. And so to get a non-trivial composition factor, you need to quotient out by scalar matrices. And this is indeed the irreducible highest weight module with weight lambda 1 plus lambda n minus 1. Okay. So why are joint modules easier to deal with? Because of their zero space. Okay, the zero space is just the fixed space of a maximal torus. And well, in general, we're not going to be able to deal with the adjoint modules just by dimensional considerations because, well, the dimension of our group H is the same as the dimension of Lie of H. So looking at the dimension of the variety is not going to exclude any cases. But if we have two elements in the zero space, they are in the same H orbit if and only if they are in the same W orbit. So W being a finite group, we know that as soon as the zero space has dimension at least 3, well, what happens? We have infinitely many singular one spaces in the zero space, meaning that we cannot possibly have finitely many orbits on singular one spaces because everything is controlled by the action of the Weil group. So we get a nice finite list of possibilities, and we can see how to deal with one of them. So when H is SL4 and P is 2, we take the trace 0 4x4 matrices, we quotient out by the scalar matrices, we're acting by conjugation. The zero space is two-dimensional, and you can just look at it as the subspace of diagonal matrices. And just some elementary arguments, looking at the Jordan canonical form, we can see that every singular vector is either semisimple or nilpotent, and in fact, there's only one orbit on semisimple singular one spaces, and in general, well, we have finitely many orbits on nilpotent one spaces in the adjoint modules. And this shows us that SL4 on this composition factors of the adjoint module has finitely many orbits on singular one spaces. Okay. So when we want to, so now we were looking only at H being a simple algebraic group, and we want to, if we want to answer, to give a complete answer in the case when H is reductive, then we need to solve the question when H is a semisimple group as well. And for now, we have a partial result. So when H is maximal semisimple, we have this small list. So these groups are, well, the first one is an SP4, SP4, and the module is just a tensor product of the natural modules for SP4. And then we have a similar SP4 tensor, some SP2N. Okay, so what is needed for us to remove this condition on maximality? And so to get a full characterization of these modules, we ideally want to find, so we're working on one spaces, we want to extend it to totally singular M spaces. And once that is done, that's gonna very quickly tell us how to solve the semi-simple case. And then we would possibly like also to find a couple of remaining cases when G is not a classical group, but an exceptional group. Some work has been done for maximal rank. There might be something left. And I think this is it. Thank you very much.
You start with a parabolic, which is a maximal parabolic.
Yeah.
No restriction
On the
finite number of double cosets.
yeah, we start with the maximal parabolic. That is a I mean, ideally one wants to look also at cases where you're just maybe just containing just a normal parabolic. That's the next step. I mean, there are there's a lot of work to be done. Yeah.
No other question? So I guess we can thank all the speakers of the week again. And of course the organizers of the workshop as well.
Maybe just on behalf of my fellow organizers, which are Mark Kapan and David Craven, I would very much like to express our thanks to all the speakers of this week. I think they have done a very great job, and I hope that some of the young people have at least got something out of this week, which will occupy them